At 5:30, let's make a start. So, the agenda for this one is pretty much just going to be exam revision. In fact, we've had a look at all of the Unit 3 and 4 stuff already, as far as like all the group classes that have happened for this year. And so Class 2 is essentially now going to be purely exam revision. We will still run through some specific Unit 3, 4 stuff very targeted in the Class 3 stuff, because that's a bit of a mix between doing Unit 1 and 2 stuff, doing Unit 3 and 4 stuff. But as far as Class 2 goes, pretty much it's just going to be now very quick fire exam revision stuff. It'll cover literally everything as far as content is concerned. This is where you're able to test your memory as far as that stuff goes. So I think probably a nice way of easing into that would be to have a look at the Chapter 19 revision chapter, because as you'll notice, it's all of chapters 1 through 18. This is basically an exam, even though it doesn't necessarily follow the exam structure. One of the things we'll see in the coming weeks will be getting very familiar with the exam structure, how tech-free looks, how tech-active looks. You'll find tech-free are very repetitive type questions. They'll look a lot similar every time you do them, whereas tech-active starts having a bit more of a the particular topics that are asked are in different orders. You can't really get a bead on what's likely to appear on a tech active, but you can definitely get a bead on what's going to happen for tech free for a decent portion of it. But okay, let's ease into the revision. Tech free. No real lecture here. It's going to be basically diving straight into questions. So, question 1. We've got f, we've got g. Write down the rule of f of g of x. Does anyone remember what any of that means?
In g of x everywhere where there's x in f of x.
Yeah, exactly right. Yeah, so every x in f is going to be replaced with g. There's nothing too crazy there. So if I go to the handwritten bit, we've now got f of g of x is now equal to 3x plus 1 all squared plus 6. 3x plus 1 all squared plus 6. You'd probably expand that, because this isn't guaranteed to be like in a factorized form. This might not be the most simplest way of doing that, so you'd probably just expand that out and call it a day. Next up, simultaneous linear. So we've got it in the scenario specifically where we want infinitely many solutions for simultaneous. What's going on there?
They have to be the same line.
Yeah, they have to be the same line, correct. When you have infinitely many solutions, it means that the lines intersect at every single point. So how are we going to force these to be the same line?
Do we equate them to each other?
Equating them to each other sounds decent. So as in what? Kx plus 3y equals 4x plus k plus 2y?
Yeah, I think so. I'm not sure then. Could be wrong.
Yeah, I don't. You could. I don't really see where you would go from there, though. One thing that's worth highlighting is that they're both linear. Because like what you suggested is fine if you're just trying to find like regular simultaneous, which is you're just going to get one x, one y. When you equate the two things together, you knock out one of the y variables. So if you wanted to do that kind of approach, you'd probably get like y or x on its own and then equate them. That way you're at least knocking off a variable. But if you do that, you're still left with two things. You've got a k and an x, or a k and a y to deal with. There is a kind of way that we can go about this sort of scenario when there's an additional parameter in there. And that's thinking about things in terms of linear, right? So linear being some sort of y equals mx plus c, it basically means that for two lines to be the same thing, the m and the c need to be the same in both. So my preferred approach for doing this is to start by rewriting both of these into y equals mx plus c, and then comparing each copy of m and c together to figure out what would it take to make them identical. Because that applies whether you do infinite solutions, whether you do no solutions, or whether you do one solution. It's always the same thing. Start by y equals mx plus c, and then figure out m and c to actually get what we're trying to get, which in this case is identical, so we try to make them identical. So rearranging to y equals mx plus c, nothing crazy there. So you're going to have 3y is equal to negative kx for the first one, and then y equals negative k on 3x. It's equation 1. I'll do it underneath actually. Then you're going to have k plus 2y is equal to negative 4x. And then finally, y equals negative 4 on k plus 2x. Huh, that's interesting. There's no plus c's in either of them, which makes life a lot easier. So the constant is already kind of sorted. They're already both 0. How are we going to force gradients to be the same?
Now do we equate and solve for k?
Equate and solve for k. Depends on how you mean by equate. There's a couple of ways you could equate. What's the next line?
Do you do like you make like equation 1 equal to equation 2?
That ends up actually going a little bit too far, because when you do that, you're going to have k and x in the scenario. Although to be fair, you're still going to be dividing. You could still work it out by dividing both sides by x anyway. So if you did do that, you still wouldn't actually be wrong necessarily, because when you do this equals that, the x's cancel. It's just that we want to typically avoid the case where we're dividing by variables, usually like the x or y, because those are typically our x-axis and y-axis. Yeah, why is it bad to divide by variables? Fundamentally, it's because you want to avoid divide by 0 cases. That's usually the main thing, but I'm not sure how much that matters when you're doing this sort of situation, because there's multiple variables. We don't actually care x solutions, we care about k solutions. So it might not even end up mattering. But yeah, all that said, the most direct way to take the bits that you actually care about, which is the gradients of each of these, and make those equal to each other. Because that's the whole point, right? We want the gradients to be the same, so we grab the gradients of each and put an equal sign between them. Solving for k here is trivial. So looking at negative 12 equals negative k bracket k plus 2. Negative 12 equals negative k squared minus 2k. That's just a quadratic. There's no actual restriction on k if you look at the question 2. There's no like domain associated with that. So whatever the solution to that comes out to be, those two solutions are your values of k. Does anyone want to see me solve a quadratic, or should we just move on? Alrighty. Next up, transformations. Find the equation of y equals 1 over x after it's applied the transformation of 2x comma negative 3y, and describe a sequence that maps. Okay, so it's both apply and describe what this means. Fair enough. All right, well, there's two parts to that. First is applying it. I'm not really fussed how you want to apply it, either doing by the recognition or by x dash y dash. What should we do? No memory for x dash y dash or transformation stuff. Okay, so this statement here that I'll write out, you got x comma y maps to 2x comma negative 3y. The most natural way of solving this is to think about things in terms of x dash and y dash because it's kind of already using that point form notation. You'd almost have to go out of your way to try and re-rationalize it so you can use the by recognition approach. This is why typically knowing this one is more multi-purpose than knowing just by recognition because it makes it harder to do these. But anyway, point is that this is your x dash and y dash. So you have this scenario that is x dash equals 2x, y dash equals negative 3y. That's the first step of applying a transformation. Does anyone remember the next step once you have x dash, y dash? If you want to apply this.
Don't we transpose so that it would be y and x?
That's exactly what we do. Yeah. So that's going to get half x dash equals x, and then 1 over, negative 1 over 3 y dash is equal to y. Nice. All right, what do we do once we've transposed?
Sub it back into the original.
That's it. Yeah. We have this statement of x, so we can replace the x with what it is. We have this y, we can replace y with what it is. So in total, we're now going to have negative 1 over 3y is equal to 1 over half x, which we can obviously then simplify. 1 over a half is just going to end up being 2 over x, and then, well, might as well keep this here, negative a third y, and then do it in the next line. Y equals negative 6 over x, just multiplying both sides by negative 3. So that's part one sorted. We've applied the transformation. The next thing it asks us to do is to describe the sequence of transformations that we've just applied. Now, there's a reason why that was said last rather than before, and that's because there's actually multiple ways you could describe this. Curious what gets come up.
Could we say dilation of 6?
Yeah, you could say dilation of 6, although you would have to say either from or along the correct axes. Which axes?
Is it y?
From y or along y?
From?
Not from. It'll be along y if you want to say y. And the reason why is because negative 6 on x is the same thing as saying negative 6 times 1 over x. So the thing that's a multiplier on the entire function is in the y direction. So you either say from x or you say along y. But yeah, we're going to have our dilate of 6 from x. I'm going to say from just because that's what like basically every other source says. There's a few that say along, but that's the most consistent wordage there. From. What else have we got?
Is it a reflection in the horizontal axis?
Yeah, that's nice and diplomatic there, using the horizontal axis instead of saying from or because yeah, you would say in a particular axis or about a particular axis. Yeah, that's a nice and easier way to say it, specifically saying the horizontal axis, because you don't have to worry about whether it's the particular wordage around it. But yeah, so negative always impacts y. So if you imagine you've got your two dots here, a negative just means you take this down to here. It's reflecting in the horizontal, but the y values are changing. So you would say reflect in horizontal, or you can just say x. Yeah, that is one correct way of doing it. The other is that you can technically also go here and be a bit more, it's a longer solution. You would say something to the effect of dilate by, actually what is that? That's going to be dilate half, no, it's going to be dilate 2 from y and dilate a third. No, sorry. Dilate 2 from y, dilate 3 from x, and then reflect in x, because we're looking at these ones instead. Now, there's no need to do that because you got the terms are condensed down here. But just an interesting thing to point out that there's multiple ways of doing the same set of transformations. Some are obviously going to be a lot more effective. All right, question 4. We've got a function, which is a cubic raised to the 7th power. Find f dash x. What's that all about? Question 4a.
We have to find the derivative.
We do, yeah. That's what that means. We're finding derivative. The question now becomes, how do we find the derivative of this particular scenario? What kinds of things we have to consider?
Can we use chain rule?
We absolutely can use chain rule. Chain rule is when we have a composite function, which we do here. We have a cubic that's raised to a power. Nice. How do we apply it?
Let u equal the inside.
Yep, let u equal the inside is correct. U equals 5x cubed minus 3x. What else?
Y equals your u to the power of 7.
That's it. Yeah. We've done our substitution, so we should now write our, there's this implied y of u here. Yeah. What else?
And then we find the derivatives of each of them.
Absolutely. Yeah. Derivative of these. Yeah. So 3 goes down the front, makes 15 x squared minus 3. And then y dash of u, we're looking at 7u power 6. If anyone needs a refresher of that, let me know. Otherwise, we can move on. How do we finish this?
And then we use the formula to like times each of them.
Yeah, correct. So formula tells us to multiply these two things together. So that's exactly what we do. So I'll bring the 7 out the front. Then you're going to have the 15x squared minus 3. I'm going to multiply by u to the power of 6, but remember that u is, of course, 5x cubed minus 3x. And so you put that there instead of the u. And that is, now specifically when I have to say f dash here, because it told us solve f dash x. If you put dy on dx, you'll probably still get the mark, but it'll not be looked on as favorably if we're competing for a, like if you're on the edge of getting a study score increase or not. That's where you would leave this. There's no real way, at least that I can see, that makes this look like this. We can't quite get them to be a common factor. And no one's expanding out the power of 6 on that in a tech free, so there's not much you would do there. You might take a common factor of 3 out of this, just so you can be a little bit of showing your work, of knowing that you see a common factor there. So what are we looking at? So 21 bracket 5x squared minus 1, and then the rest of that. At least that way you're doing a quote fully factorized approach. It's probably the nicest way to leave that. Next up, part B. F is equal to 2x e to the 4x. Evaluate f dash of 0. Very similar sort of thing. What should we do?
Do we use first product rule to find the derivative?
Sounds like a great idea to me. Yeah, product rule, because we noticed there's a product of the function 2x and the function e to the 4x. Nice. All right, how do we use product rule?
So you want to define like if you want to identify your two functions first, and that's 2x and e to the 4x.
Yep.
And so you can assign them as whatever you like. Let's say u and v in this case.
Mhm.
And you want to do u times the derivative of v plus plus v times the derivative of u.
That's it. Yeah, very good. If that was memorized, that was really good. Either way, you've also got it on your formula sheet as well. Nice. So we need both of those. These are not too bad. 4e, 4x. That's clear enough how those were derived. Cool. And then yeah.
Wait, Chris, could you just tell me about how we got 4e to the 4x?
Yeah, okay, cool. So derivative of e to the x. So when we have d dx of e to the x, that always ends up just going back to e to the x. But we don't quite have e to the x, we have e to the 4x, which is itself a chain rule, right? And so basically, if you wanted to do a very longer-winded way of going about it, you would basically set your u equals 4x. Your y of u is now just e to the u. Y dash of u ends up being e to the u again. U dash ends up being 4. And then as per chain rule, you multiply these two things together. Your derivative is therefore 4e 4x, because remember, u was 4x. Now, that's a full proof as to why we got here. It is worth pointing out on your formula sheet, you'll actually have, I think it's written with an A there. I'll fix it up a little bit actually. So on your formula sheet, you'll have e to the ax is equal to ae ax. They do these simpler chain rules for you ahead of time. And so yeah, the reason I was able to go straight forward is because I just recognize that in every case, whatever the coefficient here just drops down. But the real reason is because when you do chain rule, you're just doing diff of this and then chucking it at the front. Clear enough?
Yeah, thank you.
Nice. And then yeah, as you said, once you have those terms, you just plug them together. I mean, that's just plugging things together and factorizing. Does anyone want me to do that? Or are we happy enough with what that's going to look like now? Actually, no, sorry, we need to do continue it because it's f dash of 0, not f dash of x. Sorry. So we do need this actually. Let's not abandon this quite yet. So f dash of x is equal to 2x times 4e 4x plus 2e 4x. You can go out of your way to play with this a bit more, to factorize it, take out common factors, simplify, but we don't actually care about like simplifying f dash x because we don't want f dash. What do we actually want? That question actually asking us to have.
0.
Yeah, f dash 0, correct. So you can simplify this as far as you want. Simplify it insofar as it makes you confident to sub in 0. That's really all you actually care about. So if you can see, oh yeah, I got this 2x here, you put a 0 here, that whole thing's dead. And then, well, you've now just got 2e to the 4 times 0. Using index laws, anytime your power is 0, the exponential goes to 1. 2 times 1, 2. So you could play around with simplifying that, but you'd be wasting a bit of time if it was in a like test scenario. Fair enough. Anything to explain there further? If not, have a read of 5a and let me know where you're at on how we would go about. Like, actually, maybe not. 5a is pretty similar. Same thing with b. Yeah, okay. I mean, if there's anything in like 5 or 6 that you feel like is worth having a look at because the functions look weird, let me know. But it is still just going to be some form of product chain or quotient rule and using the table of derivatives. So if there's any of those, let me know. Otherwise, have a look at 7. 7's a bit of a tough one. You've got two circular functions in the same equation. Not particularly common, but at least not in the textbook, but more common in an exam type scenario.
Chris, is this pi over 8 plus I'm not sure if it's 2 pi n or pi n.
It might be. Hang on. So let me I can't see what that is at a glance. Let me have a look at the answer to 7. Yeah, pi over 8 is part of it, yeah. And you're determining between whether it's pi n or 2 pi n. Is that where you're at?
Yeah.
Okay. I'll tell you it's neither. It ends up being pi n on 2.
All right, because the period is changed. Yeah, my bad.
Yeah, that's actually a good way of looking at it. The fact that you've got, sine 2x cos 2x, your period is no longer 2 pi, but it's actually pi. How did you solve that? Just for my sake and Pia's sake.
Like the pi over 8 part?
No, just how'd you get any of this going? What was the goal? What did you do?
Well, because there was 0 on the other side of the equal sign, I knew you could just make the equation say sine 2x is equal to cos 2x.
Yep.
And from what I remember is that like sine is equal to cos at pi over 4 usually.
It is, yeah.
But that's when it's sine x and cos x. But since it's a period of 2, you gotta divide your answer by 2.
Yeah, because it's 2x is equal to that, yeah.
Yeah, and then I got pi over 8.
Yeah, that's going to get the pi over 8 for that one. Yeah, and kind of what you were saying earlier, remember it's general solutions, so you have to do your 2 pi n there. Although what you were saying before is that because it was, because it was, that actually doesn't, yeah, I'm looking at it now. That rationalization of why this ends up going to pi n over 2 doesn't actually hold up quite so well. Now that I'm looking at it now. And the reason why is because you haven't actually found the second way where these are equal to each other, which is at the, 5 pi over 4. There's 2 spots where these are equal to each other. So this should still be 2 pi n, and you still should divide everything by 2 to get your pi over 8 plus your pi n. However, you do also now have 5 pi over 4 plus 2 pi n, which gives you the 5 pi over 8 plus pi n. Now, the thing that gets you to having pi over 2n is the fact that you're able to combine these two into each other. Now, how you actually do that from here seems like a challenge to me. Because doing it this way, while it can work, sure, you can look at where sine equals cos, probably a nicer visualization of how these end up condensing down is doing the convert to tan technique, which is where you divide both sides of your equation by the cos. You're going to have sine divided by cos over here, which is just tan, and cos divided by cos is just 1. And so when you now see it this way, you're looking for where tan is equal to 1, which is at pi over 4 and 5 pi over 4 plus 2 pi n. Now, because it's tan, its solutions are symmetrical in pi rather than 2 pi, which is why you don't actually have to find that second solution. You can just simplify it down to just saying pi n here, and then go from there. Pi over 8 plus pi n over 2. That's how that ends up simplifying. Bit harder to see here. I guess the challenge you have to see is that these two are separated by pi. So instead of doing full 2 pi revolutions, you just do 1 pi revolutions and knock one of them off. Is it clear enough why that can be simplified further? Because you can still have this as your final answer. It's just not as simple as it could be, which is when you combine it down here. Because if you're going to go down this route of saying where to sine equal cos, I guess it is the same as saying where tan 2x equals 1. Basically, the decision you have to make is whether you want to give this as your answer or this as your answer. Both on the right, this is the higher scoring answer. If there's nothing to clarify further on that, have a look at question 8. Is this clear enough? I can pull up some notes if you want to have a look at it.
Yeah, thank you.
Yeah, okay. Cool. Question 8. Negative pi to pi, circular function, amplitude and period. I think that's going to be pretty chill for us. Oh, this is the first time they actually bothered to put double brackets on the sign and just leave the 2 hanging there. How thoughtful of them.
I mean, the amplitude is 4, obviously.
Yep.
You see.
Amplitude is 4. Nice and easy. And the period?
Is the period just 2? I mean, no, it's 1. Is it 1 and 2?
Let's find out. So period is always 2 pi divided by n, where n is 2, because this is our n value here. And so you're going to end up with just pi. Make sense?
Yeah.
Cool. That's amplitude period. Sketching this full graph. Yeah, it's going to take a bit. I'll do it if you'd like to freshen yourself on it. Just know that it'll take a bit of time to sketch the graph. Does anyone want to refresh on how to sketch a graph that's got all this shit going on?
Chris, I think I missed the lesson when I was overseas when you did this lesson around sketching graph. So could you please show me? Sorry.
Yeah, okay, that's fine. Yeah, sketching the graph. So good news is we've only got a horizontal translation. There's no vertical to worry about, so it's going to be less painful. Cool. All right, so we've already got our amplitude and period from before. Next up from there is basically setting up the array of values, right? All of our x coordinates. Now, the way I present in the notes is sort of an introduction to it, just so you have at least something. And the double reason is because explaining what I'm about to do in notes is a lot harder. So here's what we end up doing to make things a bit faster. This we would know is a shift left by pi over 6. That's a horizontal translation. So basically what that means is our starting point for the circular function is now shifted backwards by pi on 6. From there, we need to figure out the next 4 ticks so we can get our peak trough middles all sorted out. Now previously I would say just start by doing your 0 to pi, quarter it up, and then shift it. This is faster. So we'll see if you guys like this approach better. So we know our starting point is negative pi over 6. So we're going to put that here. Now, before we were used to doing a full period, halve it again. Essentially what we had was adding quarter period intervals to our thing. So we're just going to jump the gun on that and say, okay, well, we have pi as our period, so that means the quarter period is pi over 4. And so basically that means, starting from here, I'm going to repeatedly add pi over 4 separate times to get my next 4 interval ticks. This will end up being faster than getting your initial set and then shifting them all back. ends up being a bit of a pain. So, add pi over 4. This looks a bit nasty because you've got different denominators. So, good news is you only have to simplify this once. So you do your cross multiply, negative pi. Let's just get rid of this. Negative 4 pi plus 6 pi over 24. Simplify that down, looking at 2 pi on 24, which I will keep as 2 pi on 24. And the reason why is because we've already gone out of our way to simplify this, or at least change the denominator of this. Because now all we have to do is realize adding pi over 4 is the same thing as just adding 6 pi to my numerator a bunch of times. So you're going 6, 7, 8 pi, then 14 pi, then 20 pi, 1, 2, 3, 4, and 5 was our initial one. 24, 24, 24. And so you can see it ends up being a very, that shouldn't be a plus, it should be a tick. It's a very fast way of getting your next set of interval ticks without having to do a subtraction on every single thing. From here, you can then safely simplify these down because you don't need them anymore in their easier to work with form. So pi over 12, 4 pi over 12 becomes 2 pi over 6, becomes pi over 3. 14, so we're looking at 7 pi over 12, and then 10 pi over 12, 5 pi over 6. Cool. Now I'm just going to put those all down there. So we're looking at pi over 12. Yeah, okay. Pi over 12. We'll do tick, tick, tick. Pi over 3, 7 pi over 12. And 5 pi over 6. So we get our array of values that we can actually now work with when it comes to dotting out the middle peaks and troughs. Is it clear enough up until this point how we've got that array? Because it's very hard to write this in notes. Easier to see it. Alright, I'll take that as a yes. And if I'm going too fast, just let me know, of course. From there, amplitude was 4, so peak and trough being 4 and negative 4 is pretty chill. And then we've got to determine, is our starting point, given that it's sine, are we looking at a middle, peak, or trough? Who can tell me? But sine, where does sine start?
Doesn't sine just start on the horizontal axis?
Yeah, sure does. Starts at the middle. That's it. Now, the reason I say starts at middle is because you'll get to a point where you have +1 or -2 or whatever, and that means it won't be on the horizontal axis anymore. It'll be the whatever the vertical shift is. So yeah. Now, immediately afterwards, we go to a peak. So it means our next tick is a peak. Next is a middle. Next is a trough. Next is a middle. And then that's our graph. How did I miss both of those dots? Now, this one's doubly challenging because we didn't necessarily want to sketch a cycle. We wanted to sketch between negative pi and pi, which is a bit of a different beast that we now have to add on to this thing. But are we at least clear on how this first section came into being? Because this is what you have to do to start this one out. All we're going to do is sort of expand from here on it. Any questions on that? going to have to give myself some space to actually make this one work, because we're going to have to shift a fair bit backwards, because we've got to get it all the way to negative pi. So let's move this over here. Cool. So when it comes to filling out a domain, we're essentially going to go back to this and continue the pattern until we've reached negative pi to pi. So we kind of already reached 5 pi over 6 here. I can already tell off the bat that adding 6 pi to my numerator is going to push it beyond pi. So I'm not going to bother finding that next one. I'm just going to truncate it off at pi and say, in fact I'll make it in red just so we can see it's a cutoff point. And I'm just going to continue the curve up a little bit. Right, not quite to a peak level, but we know it's not going to reach a peak because the next tick to get to a peak would be much further than pi. However, backwards, there's a lot of room to grow. So let's expand that all the way out, and let's keep finding more ticks. So basically we're going to go backwards from this one now, which is subtracting 6 pi from our numerator a bunch of times. So looking at negative 4 pi, negative 10 pi, negative 16 pi, and negative 24 pi. Oh, look at that, that's actually perfect. Negative 24 pi. No, sorry, negative 12 pi. Negative 22, my bad. I was going to say that felt a bit weird. And, well, the next value would be greater than 24. 24, 24, 24, 24. And, well, you simplify those down as well when you actually put them on your tick. So we got 1, 2, 3, 4 more. So looking at 1, 2, 3, 4, and then there's going to be the actual cutoff of negative pi. These are, okay, so negative 4 pi over 24 is going to become negative 2 pi on 12, negative pi on... Okay, so that one was just negative pi over 6 because of course it was. So never mind that last one. This is negative pi. That's negative pi on 6, we kind of already knew that. Negative 5 pi on 12 is as far as that's going to go. 16 goes down to 8 on 12, 4 on 6, 2 on 3. Negative 2 pi on 3. And then 11 on 12, so negative 11 pi on 12. Cool, have that one. Minus 5 pi on 12, minus 2 pi on 3, minus 11 pi on 12, and then, well, minus pi is our cutoff. Not quite a key feature though. Well, sorry, not a min, max, or middle. So when we're dotting things out, I'm going to be mindful that when we get to that spot, we're not going to quite make it a middle, but a little bit above it. And you'll find that with these symmetrical domains, they'll cut off at the same y value. Like these cut off at the same point, horizontally speaking. And so really the only thing that's left now, because we've got our, well, there's two things that are left. One is the y-intercept, and two are the endpoints. Y-intercept is just x equals 0. Endpoints is just x equals plus or minus pi. I'll do it if you want to see how that simplifies down. Do you want to have me go through and do x equals 0, x equals plus minus pi in this to see what that looks like? Happy to do it. Fine. But yeah, you will need to do that to get the endpoints labeled and the axis intercept done. But okay, if that's good enough, we can move on. Question 9. In fact, yeah, so maybe I'll ask Pia actually, because you were there for both of them. That approach of doing the circular function as opposed to what I said earlier, which is subtracting a bunch of x values, is that better for you?
Yeah, I think it's like better.
Yeah, it's definitely faster for sure. I was just concerned it might be too confusing to get off the bat, but certainly faster. But okay. Question 9. That's just sketching a hyperbola. We can do it if you like. I don't think hyperbolas are particularly difficult, but maybe someone wants a refresher on hyperbolas. Otherwise, we can move on to question 10, which is inverses. I'll leave it up to you guys, whoever wants to shout out first for it. Question 10? Yeah, sure, go for it. What do we have for question 10? How do we do inverses?
So I think like just for like our like solving purposes, can we rewrite the function as like y is equal to 5e to the power of x minus 1 minus 3?
Yeah, certainly. Y equals 5e x minus 1 minus 3.
Yeah, and now to find the like inverse, right? So I think we gotta swap the x's with the y. So wherever there is a y, you gotta put an x and vice versa.
That's correct. Yeah, that's good.
And is it now that we gotta make y the subject?
Sure do. Yeah. Do you want to walk through that, or do you want me to just sort of fly through it a bit?
Yeah, I'll just let you take it from here.
Sure. So we're going to add the 3, divide the 5. The reason why is because our y value is trapped in the exponent. And so to free it from there, you need to get the exponential on its own and then flip to logarithm from here. Base of e means you have log e, or natural log. The thing on the equal sign goes inside the brackets of the log. So x plus 3 over 5. And then, as desired, we've taken the y down from the power into something that's actually rearrangeable. That gives us y equals natural log x plus 3 all over 5 plus 1. And there's one thing we have to do to finish this one off to make it appropriate for the answer. What are we going to do from here?
Do we need to like change back to
You're about to say something and it went to mute. I'm assuming for a reason. I'm assuming you're talking to someone else at the moment. Yeah, so you're going to change the y to be f inverse, is what I think you're going to say. So replace that y with f inverse. Yeah, you can put f inverse of x in there. Technically it says do f inverse, but putting the x there isn't wrong. You're not going to get marked down for that. Yeah, label it f inverse. And we've specifically done exactly what was suggested there, which is find the rule of the inverse function. If the keyword rule wasn't in that question, you would also have to give the domain as part of your answer. In this particular case, they've split it across A and B, but if they just said find the inverse function, you would have to give both the rule and the domain associated with it. We're going to do domain anyway. How do we do domain of inverses?
Chris, I'm not sure if this is right, but do we swap the range of the original function with the domain of the new function of the inverse?
Say that one again, sorry. It is swapping. Let me just hear that again.
So do we swap the like range of the original function with the domain of the inverse?
You probably think it right, but it's the range of the original becomes a domain of the inverse. They don't swap positions, but it is like it feels like a swap, right? You just take the range of whatever the original is and you make it the domain of the inverse. Yeah, I think that's what you meant. Yeah, that's fine. I just wanted to make it like clear for everyone. That's what's happening. Yeah, absolutely. So range of this. Is anyone at a point where they can see what the range of this is without drawing a graph? That'd be pretty cool if you're at that stage. It's fine to draw a graph though. I'm just curious if anyone can see what the range of that's going to be. Otherwise, feel free to draw a little graph to figure out what it's going to be. Let me know.
Is it -3 to infinity?
Sure is. Yeah. -3 to infinity. This is a positive exponential with a shift down by 3. So you're going to have your asymptote -3, shoots up like that. Now that's about it, really. Now, when you're saying -3 to infinity, are we using inclusives or exclusives as far as brackets are going?
Exclusive, so the round brackets.
Yeah, round brackets, correct. Asymptote can never actually be the value. And so, yeah, domain of this is going to be from -3 to infinity, which in most cases, you can also look at this and figure out what it is. Like, unless there's an other restriction applied to the function, like if this is defined for all, if it's defined maximally, then this one should also be defined maximally, broadly speaking. And so if you have a look at what's actually going on there, shift left by 3 would set your asymptote at -3. So it kind of makes sense as a little like mental double check, like, hey, okay, it does actually make sense for the function. Whereas if this did have like a restriction on it, like let's say it's only from 0 to infinity, you'd have to figure out what that is and then work your way back. Cool. All right. Getting through a decent amount of questions actually, which is good.
Chris, just a question about the last one that
Yeah.
we just did. Is there like any sort of way that you'd want to notate the range? Like,
Yeah, that's always a weird one. Like, what do you say is
because
the range?
like I don't obviously because I'm in year 10, I don't do methods, so I just wanted to know if there's any specific way. Like I know like sometimes it's like X is, and then they put the E looking symbol and the brackets, and then they say X is like all integers or all real numbers and stuff.
You could probably just say this: y is an element of -3 to infinity. But you're right; it is like much more common to have domain with that notation, and range is pretty much like never given this notation. But as long as, yeah, let's see. I'm debating on whether or not you say f is an element of -3 to infinity or y is an element of -3 to infinity. I think as long as you've done some sort of statement that says f of x equals y, you could choose either. Either way, they're going to know what you're saying, which is the set of elements y. Yeah, you probably default to whatever is given in the question. So if it's f of x, you would say like f is an element of -3 to infinity.
Yeah, so since we're doing domain here, would it be X as an element of -3 to infinity?
Yeah, so when you go here, like the better solution for it, which I should be a bit better about doing, is yeah, you would say x is an element of -3 to infinity. Yeah, that's the most accurate way of describing that.
Oh, yeah, because I felt like maybe there's some people who might be a little pedantic about that. Like,
Yeah, no, you're absolutely right. It's a good point to bring it up. Like if I'm showing you stuff like like this to simplify. Oh, no, there was a weird one that I showed at some point to, yeah, like stuff like this, factorizing, taking the 3 out. Yeah, like it's definitely a really good point to bring up. So thanks for that. I did kind of be lax on that one. But okay, that's that. Question 11 is another solve for circular functions. We've kind of already touched that. So I think I'll leave that one, unless someone wants to see it. Otherwise, question 12, I don't think it's particularly challenging, but it's definitely something that comes up in Tech Free, so I at least want to see if you guys are decent with it. So you got g of x is 5x squared, but then you got this whole prove that you have to do. Yeah, have a think about that. How would you go about this? Question 12. these kind of show that's a fairly common. I'll give a hint, which is basically you wanna rewrite the left-hand side and the right-hand side in such a way where they look identical. That's the overall goal. If you can prove the left equals the right, you've successfully shown that. So with that little hint in mind, how do we start rewriting those left-hand and right-hand sides? Challenging. That, or you guys are just working on it on your own. Yeah, so basically, what I would do is I would separate both of these as their own individual problem statements. So you have this statement, g of x is 5x squared. You have this left-hand statement, which is g of u plus v, g of u minus v. And so basically you would just expand that out based on what g of x actually is. So g of u plus v is therefore going to be 5 bracket u plus v all squared, because you're replacing every x with u plus v. Come on, focus up, please. Yes. And then you're adding that to g of u minus v. So exact same thing, 5, but this time it's u minus v all squared. That's our left-hand side. As for our right-hand side, we have 2 times g of u plus g of v, so basically 5u squared and 5v squared. We need to make left-hand side identical to right-hand side. One of the things we're noticing is that right-hand side is just u squared and v squared, whereas left-hand side is u plus v squared and u minus v squared. So the way to start making it look more like the right is to expand this out. So you'd have 5, let's even put 5 all the way out the front for both of them. So we're looking at this one, which is now u squared plus v squared plus 2uv. That's that one. And then this is the same thing, but you've just got u squared plus v squared, because the u and negative v cancel each other. That's the second set there. Still got the exact same right-hand side. We'll leave that as is. At least now we've got u squared and v squareds to work with. Was I wrong about this? Do these not cancel? U squared negative uv. No, they don't cancel, do they? Minus 2uv. You got u squared minus uv minus vu. Yeah, they don't cancel. I don't know why I thought that. Because I was going to say, how are we going to cancel this when there's these? But anyway, so 5 at the front. Got a u squared here, a u squared here. That makes 2u squared. V squared here makes 2v squared. Then the others cancel down because you've got positive 2uv, negative 2uv. This from before, 5u squared, 5v squared. You can probably imagine how these are going to end up looking the same. Put the 2 in there, put the 5 in there. And then, yeah, those will end up being the same. 2 times 5 works either way you do it, whether you do 2 times 5 or 5 times 2. That's about it, really. If you want me to clarify how that kind of question works any further, feel free to stick behind for a bit. Otherwise, I'll let you enjoy the rest of your day. Take care.
Thank you.
No worries.